Or you can also use this as a second derivative.
I was going to definitely get a shot because we made it. And then
He's not talking. My how small classes gone. And you guys, I'm making this example out of thin air. I don't know how easy this is going to be to finish. I'm making my numbers up as well. But it's a pertinent question, isn't it? I got a box with an open top. And I'm trying to find the dimensions of this box that will maximize total volume if it's the case that the perimeter, if it's the case that the surface area is fixed at whatever that number is that I made up. Oh, I got to put in dimensions. How about just x, y, and z?
That looks like a lambda.
That looks like a lambda, sorry. And that wasn't even Eric.
I'm telling you, I'm telling people.
Yes, you are. And you guys, the way I start to cross solve, I know I've got a couple equations to run. My thought process is I just simply start off writing down a function that gives me whatever I'm trying to optimize, in this case, of the volume. So looking at my pretty picture, I think the volume of this rectangular solid is simply going to be x times y times z. Do you guys agree? Yeah, I'll wait.
Is this a new section or is this something from last?
Actually, I'm just finishing discussing what I talked about last time. It's just, as I recall, I didn't finish up with an example of an application. And by the way, before we're done today, I will have completed the next section. That's why I don't want to give a quiz today. So, using my second derivative test, let's come up with the derivative of the volume with respect to you know what we discussed last time, the second derivative test.
Yeah, give us some finish. I think it's like finish up a drawing question.
Okay.
Partial with respect to x and partial with respect to y.
Yeah. Do you see my point? So I think with the example I just made up, I failed. I can't use a second derivative test. I've only applied the function to two variables. So I can't answer this question right.
Can you make like one side constant?
Nice. Maybe not one constant. Maybe I can take that constraint relationship that the surface area is fixed. Maybe I can use that to maybe, I don't know, replace z with an expression in x and y. Then I will transform this function v into a function of only two variables. Do you guys see my point?
Yeah.
All right. I'll take a break then. I'll erase this. I'll pull out a piece of scratch paper. And I will use that other information, which was So the surface area is fixed at 12 square feet. But if you take a peek at my pretty picture, I think the surface area is described as, I don't know,
2xz
2xz
plus 2yz
plus 2yz
plus xy.
plus only one xy because it's got an open top. And if I were to solve for z in this equation, you guys tell me if I'm using my math skills too quickly. Wouldn't that merely give me a 12 minus xy all over 2x plus 2y?
Yeah.
One yes. Do I hear more?
Yes. I'm not going to give you that.
You're not going to give it. Well, I agree with them. And so coming back in, making a substitution, I now have that v as a function in only two variables is nothing more than x times y times that garbage. All right, you guys, no tricks this time. I think now I can differentiate v with respect to x and with respect to y. And before I compute those derivatives, what would I do next? What would I do next? Maybe you're stalling me because you came to class last time. Did I assign you homework on this? I did.
The last.
Be honest with me. Are you guys caught up with homework?
No.
No.
No chance.
Got it. What I was hoping you say is this. Next, I'm going to compute the partial of v with respect to x, then with respect to y, and I'll set each of them equal to 0, and I'll solve that system of equations. That's where I need to go next. Can I erase the question? I'm running out of room. I'll do just that. I will compute the partial for v with respect to x, and here's what I get. Egads, nasty business. But I do maintain the quotient rule says I get whatever's downstairs as is. Times derivative what's upstairs. Yeah, just 12y.
Minus 2y squared x.
Very nicely put. Minus what you see upstairs as is 12xy minus x squared y squared. Times through the bottom with respect to x, but that's just simply a 2. All over what the heck you see downstairs. Twice. You guys, so far so good? What's next?
With respect to y now?
Well, true, but I want to clean stuff first. You're right. You're right.
Ew. This is fine.
What would you do to clean it up?
I just leave it like that.
But if I'm going to set it equal to 0, I think it'll make my life easier to clean it up. Oh, come on, you guys, it's just math, D. You'd probably pull out a
All I
factor
pull
of.
out is a y.
Two can come out of everywhere.
Well, I think I'll pull out a 2. I can pull out a y. Can I pull out an x? Can I pull out an x?
No.
No. But I can pull out a 2 and a y. At least in the numerator. And I think here's what's left over. Is that an x plus y times, is that a 12y minus 2xy squared? I made a mistake, didn't I? I said pull out a y. I didn't. Shoot. But now I
You
did.
also pull in a
So
two,
go
oh,
to
sorry,
6
never
y.
mind. No, you already got it.
Well, I pulled a 2 out of the first factor.
Oh,
You're right, you could have pulled out the second factor, but leave it in the first factor. It doesn't make any difference. And let's see, I forgot, I pulled out a 2 and a y. That leaves me left over with just a, is that a 12x minus x squared y? Well, at least upstairs. And that's going to leave me downstairs with a 2 times x plus y squared times my y times the stuff. Sorry, you guys, I have no idea what the stuff is. I got to crank it out. Does that give me an the first times the first, plus the outside times the outside, plus the inside times the inside, plus the last times the last? Some said no.
Yeah. It'd still be a 2 on x.
If you're, with the 12x, wouldn't it decrease to a 6?
No.
Because you're pulling out a 2 from 12. Yeah, that part.
That's fine, and then you got a 2 left over here. I just pull out of the first factor instead.
Oh,
But it doesn't matter, either way you put it, it's going to be the same thing.
Okay.
I pulled both 2's out, canceled one of the 2's upstairs and downstairs, left with one left over downstairs. Is that okay, you guys?
Yeah, you can still pull a two.
Yeah, that's my confusion. You can pull another 2 out, that's what I'm saying, and then you don't, make your life a little bit easier, I guess is what I'm saying.
No, there's no two in the last two.
I don't think I can because when I read with the parentheses over here, notice how the very last term does
Oh,
not
you
involve
hadn't written the
factor
last-
x.
Oh, okay.
Yeah, I was just cranking out the product of those 2 binomials.
Okay, sorry.
You didn't have
That's
the rest
my
of
right.
it yet. Okay.
I don't. I have no idea, you guys. This cleans up nicely. I really don't. I've got a y times the, let's see, is that, the 12x cancel? That was nice. Does that give me a negative 1x squared y plus 12y minus 2xy squared? All over stuff. you guys, you gotta confess, now that I canceled the 12x and the negative 12x, I mean, when I look at that mess upstairs inside the brackets, I really can at this point pull out another factor of y, can't I? Does that give me a y squared times negative x squared plus 12 minus 2xy?
Is that a 2 or a 0?
Where?
Right there.
X plus y squared.
The something power.
On the bottom.
Square.
It's a square.
It's a square. Sorry.
You're right, Eric, you trained everybody well. What's next? So the zeros my denominator are. I think,
There's no zeros in your
yeah, I think
denominator.
they're irrelevant. Because when you look at the zeros downstairs, it suggests that y is equal to negative x. I'm dealing with a box, and so I'm not gonna have negative quantities. I think I'm gonna reject any critical numbers coming from the denominator. As far as the
Well,
numerator is concerned, I don't
If
know.
your x and your y are both equal to
Could
zero.
you say that one more time, because I
Yeah,
totally
Eric, I'm
brought
sorry.
it in my head.
Yeah, tell me to stop talking so fast. I just maintain I'm gonna yield no viable critical numbers for my denominator, because if I set my denominator equal to 0, it simply means y is equal to negative x, and that means x and y have opposite signs. And since x and y are both dimensions of a box in 3 space, one of them can't be negative.
Oh, okay,
See my point?
because they're both real.
And Bradley just brought up a good point. It is the case that both can be 0, but if both are 0, that means I'm not maximizing the volume, so I can reject those.
Okay.
We don't have a box that goes here.
We'd have a box that's, yeah, completely flat.
Are you
They'd be
worried
in two
about,
dimensions then.
wait, why are you even worried about what the denominator is? Because aren't you gonna be setting this to 0?
Well, true, I'm just saying, since my denominator is never gonna be 0 realistically, I can get rid of it and multiply both sides by it. I'm just saying it's irrelevant.
Don't you have to do the partial of y also?
Why? That's the word point, not the letter y. Why?
I'm not sure, just.
No, it was a question for the class, why?
Because we needed to compare when they're both equal to 0.
Yes, because I think the critical points come from when the partial of v respect to x is equal to 0, and simultaneously when the partial of v respect to y is equal to 0. Do you guys see my point? So yeah, I have got to finish. However, before I do finish, do you guys agree, I'm running out of room, can I erase this? Do you guys agree that v sub x is equal to 0 simply when y is equal to 0 or my negative x squared plus 12 minus 2xy is equal to 0 as well? You guys, can I cross this out? Again, if y is equal to 0, I got a flat box. I'm not going to be able to maximize this volume. All right, so I've got some work to do. I now have to come in. Oh, shoot, I can't. You guys, I erased my v. What was v? Can somebody tell me? I'm sorry, I've erased it.
X, Y, Z.
X, Y, Z. No, I mean after we substitute
Oh, x, y times 12 minus x, y, all over 2x plus 2y.
My apologies.
You're forgiven.
Thank you. So now I'll come in and compute the derivative for v respect to y. Oh, I'll try to get it high. I need room. And that's not enough room. Cheaters. I think that's going to tell me that I get my denominator. As is. Twice. Times the derivative of my numerator with respect to y, but that's going to be the first. Times the derivative of the second. You guys, mind if I don't do this? Can I stop? I'm kind of tired. I make silly mistakes. As I differentiate, do you mind if I expand that numerator just to make my life a little easier? Because I don't want to have to use a product rule here. Now let me finish up my process. Using the quotient rule, the derivative of this ratio is the bottom as is, I got it. Times the derivative of the top, I have no idea where the square came from. Times the derivative of the top with respect to y, isn't that just a 12x? Is that a minus 2x squared y? Minus the top as is, don't touch. Times the derivative of the bottom with respect to y, that's just a 2. All over my denominator squared. And if you guys want, I won't ask any questions. You relax and allow me to massage with my mathy skills to simplify this particular nasty looking fraction. Yes?
That times 2, that.
It is times 2 at the end because it's multiplied by the derivative of the bottom with respect to 1. here too, everybody, to help myself clean this mess up, I will indeed pull out a common factor of 2. Hold on, I'm a little slow. Also a common factor of an x. And I think here's what's left over. Thank you kindly. Sorry, I gave a partial take-home for the Math 33 exam, so people are going to come in and drop it off. And if I pull out a 2x in the first group, does that leave me with an x plus y times, yikes, instead of 12 minus 2xy, minus the quantity which is, I pulled out an x, didn't I? Instead of 12y minus xy squared. Whoops, I forgot my denominator.
Got your closing parenthesis also.
Thank you very much. You're catching me on that a lot lately.
Because you do it a lot.
Thing.
Yeah.
I never used to do that. And a tad bit of cancellation. With the 2's, that leaves you with an x plus y twice downstairs. And a remaining factor 2. Oh, factor of x remaining upstairs. And let me deal with what's on the inside. You guys, I can't see any tricks that I can pull out. I just gotta come in here and crank everything out, those products. So, here's the first times the first. Here's the outside times the outside. Here's the inside times the inside. And finally, the last times the last is a minus 2xy squared. And what's remaining on the other side of the subtraction operation is that going to be a minus 12y plus xy squared. You guys, I'm nervous. I mean, this really does look like a mess. It's time for me to panic. Shoot, the 12y's cancel. You're right, I've got a couple xy squared terms. They don't cancel, but I can combine them. And I think that leaves you with an x times, is that a 12x minus 2x squared y minus a single xy squared, I hope. All over this.
Do you,
Yes,
the 1, the 2's,
Can you see that one more time?
3, the second one to the third one, there was a 2 on the far left.
But I pulled both 2's out,
Oh, you pulled.
and I
both.
canceled one. And one remains downstairs. As a matter of fact, at this stage of the game, you guys, can't I come in and just, also here at this position, pull out a factor of x. I think that leaves you with an x squared times 12 minus 2xy minus y squared. All over stuff. But now, if I set that partial with respect to y equal to 0, I think setting the partial equal to 0, I get rid of this. X is not going to be 0. I get rid of the denominator, multiply both sides by it. I think I generate an equation which looks like a 12 minus 2xy minus y squared equals 0. Okay, guys, I'm not kidding. At this stage of the game, I really am panicking. Because as a mathematician, I don't have one single technique to give you guys to solve a system of nonlinear equations.
Wait,
Yes, I will.
X squared.
so you simplified it there from there to there?
No, what I did was this. Inside my big black box, this is the partial with respect to y. I set it equal to 0. I neglected this factor because using the principle of zero products, this equals 0 or this equals 0, but x being equal to 0 is irrelevant. It's not yield to max. And so when I set this equal to 0, that's exactly where my second equation came from. This right here is setting v sub y equal to 0. This right here came from setting v sub x equal to 0. I said v sub x. You know what I mean, the partial with respect to x.
Does it help to subtract the two equations?
Often, yes. In this particular example, yeah, because it means the 12's cancel. It's not the only way you can look at it.
Two xy's cancel.
I agree completely.
Well, I was just gonna say use substitution, but
But if I
Yeah, yeah,
subtract
that's
one
what
equation from the other, or substitution doesn't make any difference, does that give me a negative x squared plus y squared is equal to 0?
that's a hyperbola. Alright.
Unfortunately not, because the constant's not gonna, it's non-zero. I misspoke. It's not because the constant is 0. But I do think this suggests that y squared is equal to x squared, so y is equal to x.
Really quick,
Yes.
can't you only cancel one of those, because you add the equation, you cancel the xy.
did make another mistake, an algebraic one. I should be having y being equal to plus or minus a component of the square root of x squared. It's just that, yet again, you guys, I know y and x can't have opposite signs. That wouldn't make sense in this particular problem situation. So I neglected the negative component of the square root. Holy cow. I didn't answer the question. I don't have a critical point.
Well, don't you have a collection of critical points?
I don't know. All I know is that whatever x is, y is going to be the same. So technically speaking, I still haven't counted the critical point, and there might be a little many.
You just plug in y for x.
Into what equation?
Or original?
Maybe not the original one, but how about one of these equations right here, where the partials are set equal to 0? Let me just pick one. Let me pick the top one. And if I substitute x in for y, rewrite in that first equation, doesn't that give me this? If I'm not jumping around too much on the board, doesn't it give me that negative x squared? I can't read that far. Is it plus 12? And is that a minus 2x squared is equal to 0? But that simply means that x squared is equal to 4. Oh shoot, come on, it can't be that nice. I made these numbers up out of thin air. I'm so disappointed. So I think my critical point is going to be located at 2, 2. I don't know what's next.
Find the z,
What's that?
plug that in for the original equation, find the z, find the max minus.
Okay, I'll buy that, but technically speaking, you guys, shouldn't I actually come in now and use a second derivative test, compute my determinant function, the d function? Remember what that was? A second partial of f respect, sorry, second partial of v with respect to x times second partial of v with respect to y minus the mixed partial for v squared.
Write that down, please.
Yes, I will. I'm saying this. Shouldn't I evaluate my d function, which was defined as the partial of f, sorry, I keep saying f, this example is v, isn't it? The product of the second partials minus the mixed partial squared. And if this d function at the point 2, 2 is strictly positive, then I can look at the second partial of f, or v, excuse me, with respect to x, and see if it's positive or negative. See if I get a local min or a local max respectively.
So we're checking that we get the right answer?
Well, that's what I should be doing. I'll talk about it in a minute. Here.
The problem with that is like taking the second derivative
Thank
function.
you. Is everybody okay with me not doing that? Now, I really should, but look at my first partial v respect to y. I gotta differentiate that again. So let's play a different game. Only because I got really, really lucky. If I got a box where x is really, really close to 0, don't you guys agree I get a really, really narrow box? I think its volume is going to be really, really close to 0. And if I allow x to be as big as it can be, that means either z or y are going to be really close to 0. The volume is still going to be really close to 0. So I think it's got to be somewhere in between those extremes for x for which I maximize the volume of my box. But I've only got one critical point. It's got to occur there. I got a little lucky with this example. Number one, I want to stop. I don't want to compute the d function because it's too much work. Number two, I don't think I have to because I only got one critical number. I do know there's a combination of x, y, and z values that will indeed maximize the volume of the box. So I think I can mathematically hand wave in this example and say I'm not going to compute the d function, not formally go through the second derivative test. I think I'll stop. Well, partially stop. I did ask for the dimensions, so I guess I do need to come back and compute z. But you guys, I can't. This problem took up so much board space, I yet again erased what z was. What was z? Not v, but z. I don't remember. It was a fraction.
12 minus x,
12 minus x, y.
2x plus 2.
Gotcha. So to find the corresponding z value, wouldn't that give me a 12 minus 4 all over 8? So I guess the dimensions that maximize the volume of the box are going to be 2 by 2 by 1. X and y are 2, but y is equal. Excuse me. X and y are 2, but z is equal. You guys are really quiet. Is that okay?
That whole thing that you raised, was it that the d equals vxx times vyy equals vxy squared? Is that it?
That was my determinant.
So, it seems to me a little immaterial to do the whole second derivative thing to figure out, like, let's say we got like 4 or 5 points that maximize it, you know? Or, like 4 or 5 potentials, I guess is what I'm asking. Wouldn't you just be able to plug in those individual points into the volume equation that we got, and then whatever that largest volume is, that's gonna give you what we know the points that are gonna maximize it out?
We used a plural of the word point.
What?
Used a plural of the word point. I only have 1 point.
No, if we got like multiple sets of points, I guess
Oh, I
is
see.
what I'm asking. So
You know,
like,
you gotta
let's say
get
we have
point.
like, your maximization ends up being like a cubic function, so you have blah, 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 blah,
Yeah.
blah, and blah, blah.
But that would only work, your argument, as long as you knew that with negative x, y, z values, you're not gonna use a local extrema. I got a little lucky here because of the application. I knew x, y, z couldn't be negative. And so, as long as you could do that analysis, yes, you're absolutely right. If you had multiple critical points, you could just check to see which v value is the biggest for those ordered triplets. I agree.
I hope we're not that lucky.
And we
I don't
want to
think
be
we'll
that
ever
lucky,
be
that
that
makes our
lucky
lives
on this
easier.
test.
Well, if you're this lucky, you had to go through a lot of Math 30, didn't you?
Yeah.
Math B.
Wouldn't you rather have a smaller version of Math 30 and go through the D function? I hope you would.
So, well, that's basically the same question. You keep saying that we're really lucky in this example, but what if we're not lucky on the test? Like, what would not
Oh, you won't
lucky
be,
look
you won't be
like?
that lucky on the test. Just you go through what I did last time in class. That's why I gave you so many examples of computing the D function and using the second derivative test. I just wanted to give an example where I made up my function out of thin air, but the process I'm going through is the same process I went through last time. I just think this was so horrendous with my second derivative function, or my second partial, excuse me, that I gave up, if that's okay.
In the beginning, when we started with our volume function of x times y times z,
Yes.
we had to restrict it back to 2 independent variables, which just seems like a step up from restricting it down to a single independent variable versus,
I agree. I agree. It's just, I didn't have another constraint relationship to bring it down to one variable. It'd be nice if I did. If I had a second constraint relationship to whittle it down as a function for b in terms of just one variable like x, now I can treat this like a Math 30 question. Good
Well,
point.
My question is, what happens, how do we deal with situations where we don't have those constraint relationships, where we have to deal with it with higher numbers of variables, because at this point, we're stuck with 2 independent variables, and same way.
Thank you. That was the point behind this example, is that you and I restricted. Well, it's another 60 seconds. That the second derivative test only applies to functions of 2 variables. Yeah. But we'll get out of the restriction. I promise. Anybody else?
So I was just wondering if you went through the whole process with the D and the partials and that, would you end up with the same critical points?
Oh, yes. As a matter of fact, I already found a critical point. Well, I found a single critical point. And so that's completely done. Now I go through the D function, evaluate it at that critical point, and see if it's positive. By the way, it will be. And then once I do that, I realize 2, 2 yields a local max or a local min. Oh, I don't know which. So I gotta compute the second partial for f respect to x, and see if it's positive or negative. If it's positive, I'm concave up and have a local min. If it's negative, I'm concave down and have a local max. That's what the second derivative test says. And we had a lot of examples of that last time. Eric?
I was gonna say, well, don't we know it's gonna be a max? Because if you look at the whole volume equation that we derived, it's negative x squared, y squared, those are both always gonna be positive, so.
I know, that's why I'm saying kind of stop here, because we know what this particular example is gonna happen.
Okay.
I said it differently.
Are you painting on my beautiful 3D geometry?
Oh, I should put it on the board. The document camera. This is gonna make me look so good.
It's a lot like the trough.
Yes. You guys, can I erase this?
I will never forget that.
It's okay. Neither will I. That's what a trough actually looks like, though. That's the thing.
Well, it's like that. It has like things pointed up.
Yeah, that's what my trough kind of sort of looked like.
No, it looked like a giant. It looked like a.
It was like a triangle in 3 dimensions. Imagine like a pyramid upside down with stretched out sides. That's what took us 3.5 days to solve.
You angle the sides?
Yeah, he drew it.
You didn't, from the top to the right.
I'll draw it out.
Imagine like 2 triangles like this, and then a line, like these sides go together.
So they were up and down?
I can't even.
That would be easy. So
No, we was not with the constraints we had in the problem. That was what made it hard. You couldn't actually solve it. Oh, so Malachi, are you ever gonna give us the eating bean dip equation?
The which one?
You remember?
No, I don't. What did you say?
The equation about eating bean dip at a line of ln x in 3 dimensions? Well,
Was I here that day?
yes, you were. One time Stan and I were bored, so we invented some equation that had to do with eating bean dip. And you were like, you know, to be able to do that, you have to do a vacuum or something and suck the bean dip out at exactly ln x. And like you're like, this would be a hard 32 question. I should put that on one of my tests.
You gotta tell me after class. So you guys, check this out. I have in black level curves for a surface and free space. And I want to maximize the z values on the surface and free space subject to the constraint of a curve in red in the xy coordinate plane. Now, would you guys not agree on my picture? I can maximize the z value in the surface whose level curves are given in black, subject to the constraint of living on the red curve in the xy coordinate plane at this particular point right here.
To maximize?
To maximize z, whose surface has these black level curves, so it's equal to 4, 3, 2, and 1.
Oh, so we're looking into a valley almost? It's getting
Yeah,
steep,
we're looking into a valley where here's a bottom.
So that's like a topographical map right there.
You could treat it as such, if you want to think of it geometrically.
The red line's like heading into the other one.
Well, that red curve's in the xy coordinate plane. And I'm just saying, if I live on the red curve, what z values are maximized, given I've got the constraint of living on the red curve? Wouldn't it be at that point right there? Now, notice something interesting about that point in black. I think the point has a quality that the gradient vector for the level curve looks like this. But the gradient for the red curve looks like this. Aren't they going in the same direction? Well, if they are, then I got a whole new technique for optimization given some kind of constraint.
Wait, say again, what we're doing at the.
Yeah, this is really important. I want you to catch this because this explains exactly why I'm going to use a new process I'm going to give you to in the next example. So listen to my choice of words. Everything you see in black are just simply level curves for a surface in 3 space. So when you look at this point right here on the surface in 3 space, it's going to have a z value of positive 4. Because in black, here's my surfaces equation. It's just that, what if I've got some kind of constraint relationship, a curve living in the xy coordinate plane, say something that looks like a g of x comma y being equal to 0. That's an equation of x and y. Now, subject to the constraint that I live on the red curve in the xy coordinate plane, at which point on the red curve do I actually optimize the corresponding z values on the surface in 3 space whose level curves are given in black? I think clearly this point right here on the red curve has a quality, that the corresponding z value on the surface is max. There.
So basically, it looks like this, and then the curve we're talking about is looking more like in this direction.
No, I think the surface looks like this. And if this is the xy coordinate plane, what you see in red is simply a curve in the xy coordinate plane. Now walking around on this curve in the xy coordinate plane, keep walking and walking and walking, where are you going to stop so that you get the biggest z value on the surface when you look up? I think it's going to occur at this point right here, where these two gradient vectors are parallel to each other. Can I see that differently? It's going to occur when the gradient for f is equal to, I don't know, can I say a submultiple lambda times the gradient for g? Subject to, I can spell subject, I really can. Subject to the constraint relationship that g as a function of x and y is simply equal to 0. Gosh, I guess setting these two gradient vectors, since their vectors are equal to each other, that means the corresponding components are equal to each other. Shoot, I'm looking at 3 equations and 3 unknowns.
So you're saying it's just when the direction vectors are the same, the gradient vectors?
I wouldn't say the same, I'd say parallel, or going in the same direction.
direction.
Or in English, use my MACD language, one is a scalar multiple of the other.
So, but potentially at any point, they're gonna be in the same direction.
Oh, I disagree completely. Check this point out right here. I think the gradient vector in black looks like that, but the gradient vector in red looks like this. So I disagree completely that at any point the gradient in black and gradient in red are going to be parallel.
When Oh, okay.
Because the gradients are perpendicular to the tangent planes, aren't they?
So you'd be going down on both sides.
I suppose.
I'm confused about, because we did the gradient of a three-dimensional surface is two-dimensional,
Yes.
but you're showing us the gradient of something that's already two-dimensional, the red line.
Well, that's fine, because check this out. The way I wrote things, I'm thinking of the g as a function in two variables. So when I compute its gradient vector, it'll have two components. Oh, but shoot, look at this. F is a function of two variables as well. So when I compute its gradient vector, it's going to be a vector with two components. So I think if with everything I'm saying it makes sense. I think what you're thinking is this. As an equation, this only involves two variables. As an equation, this involves actually three variables. But once I set z being equal to a function of two variables, I can treat this as a function of two variables, just like that's a function that's in two variables. So I think my sizes are actually valid, and they do match up.
Why does the g, g of x and y have to equal 0 for this thing to work?
Because I want to force it to be a curve in two space.
Okay.
If
I
you don't
guess-
like what I'm saying, if you take your g function and set it equal to some other constant, that's fine. Because when you differentiate, it's going to go to 0 anyways.
Okay. Just, I want to, can I give you like a real world example so this it makes sense in my head?
Oh, if you have to.
Okay, so.
Dirty mathematics.
So we're in a cave, and the
Yes.
idea is if we walk along any area on the surface of the cave and look directly up, what point is going to give us the highest ceiling? That's kind of what it seems like you're saying to me.
No, I think I'm asking. Okay, I don't like how you're saying I'm in some kind of valley and walking on some curve, because that curve is going up and down. I'd rather say I'm in a valley and I'm using my imagination. Going down to some plane downstairs and looking at a curve down there. And from there, ask myself, at what point on the surface, walking along that curve in red, would I get the highest C value?
Yeah, that's exactly what I said, but I say it's a cave instead, because caves are going to have a dome, three-dimensional shape on top.
It's a perfectly level cave.
Yeah,
It's a perfect
perfectly level
cave.
environment.
That's what I was missing. That's what I was missing.
That's what I imagine. I imagine like the Moaning Caverns, I don't know if you've ever been there.
I have.
It's really cool, you should go there. Anyway, so
Let's
that's,
say it.
it's in California, it's only like a 45-minute drive from here. Look it up, I don't exactly know how to find it. Anyway, so like that's what my imagination is telling me that you're saying.
I like it. I like your interpretation.
Okay.
Oh, by the way, this technique, I only have half an hour, jeepers. This technique's got a name, it's called Lagrange multipliers. I know it's nasty, professors come in, they give personal stories. I can tell a small personal story though. When I moved to California, I applied for faculty position in Sacramento, and they were interviewing me, and one member of the committee asked, okay, are you now ready to give your presentation on Lagrange multipliers? And I wasn't even thinking, I just looked at her and I asked, you mean Lagrange multipliers? I stuck my foot in my mouth so badly. I still got the job, but...
Which school was it?
I moved at that time from, gosh, I don't know, Connecticut to take a faculty position at Cosumnes River.
Consumers River?
Yes.
Mine should be